talk about Gijs Verdoes Kleijn, to give his full name, is talking about another project which we're doing in Groningen together with ESA on detecting near-Earth objects. And he is going to give you a show on this. Gijs.
Yes. Is my mic on? Yes. So to heighten the stress on my operating team together with Reese that we're leading, I have a combination of full dome and normal slides. So I will buy them beers later after this conference for this. It's a pleasure to give to you the presentation, short presentation, information exploration and near-Earth objects. So I'm Gijs Verdoes Kleijn, an astronomer at the Kapteyn-Astronomical Institute here in Groningen. And I'm giving this talk on behalf of the whole team, the Kapteyn-OmegaCEN Astronomical Science Data Center and Center for Data Science Systems and Data Science. And it's a pleasure to give it in this dome because it's one of the best places that I know in this universe to convey to you the perspective that I will be taking. And as Charlie Lineweaver said, you know, when you propose a view, you have to also make clear where your viewpoint is. You have to open your cards. And so my viewpoint on Earth is by moving out from it quite a bit and then looking down on it. And then what I see, if I'm not, you know, part of that Earth anymore, I see like a spaceship that is drifting through the Milky Way, and it has done so for a couple of billion years, and it will continue to do so for a couple of billion years more. And this, what you see around you is an artistic rendering by an artistic mathematician called Stephen Dick that created this for me. The idea is that I really will look, you know, from the outside. And when you see this spaceship drifting around, you know, it encounters all kinds of things, which I will call in short cosmo weather. And one of those is shown here. That's a near-Earth asteroid Ryugu, and that is hanging around like a sword of Damocles. But I will come back to that. Next slide, please. Full dome slide. Yes. So when I started to prepare for this short and light presentation, I was thinking, okay, what I see, you can show it again if you want. Yeah. Is that, you know, we're actually living in a special era on this spaceship because to my complete surprise, I talked to my fellow biologists, we seem to be the first ones that are downloading the universe down to on our ship. So we're downloading this massive load of data and then trying to distill knowledge and information from it. And while hearing here in the conference, but also thinking a little bit about this, to me, that gives a little bit of a parallel. It's a very rough metaphor parallel of like lossy data compression. Because we have all this data, and then we as humans decide what could be interesting to us, and we call that often metadata, and then we start to detect patterns in this metadata, and so we throw away all the bits that we think, you know, are not important, so in that sense it's lossy. And then when we find these patterns, we understand, we try to compress them down to laws of physics, and we get an understanding about astrophysics, physics in general, astroparticle physics. We think about the universe and astrochemistry, and in the end also astrobiology. And so this kind of data compression, lossy data compression, I just made a playful way of showing that. So next slide, please. So the outline of my talk is that I will first talk about these systems that we're using here in Groningen together with these large collaborations like Euclid to, you know, download this universe in some sense and then distill information and knowledge from it. And so then I will zoom in afterwards on this project that we're doing together with the ESA Planetary Defense Office. And then I will draw some conclusions. Next slide, please. Yes. And so here we again have this downloading of the universe. And this is just a playful example. You can see that there is a repeating pattern here. And if we go to the next one, we just converted from binary notation to decimal notation. And then the next slide makes it even more easy. And then you see that, you know, it's getting there to what we're seeing actually, that the message that the universe is sending us in this case is, if you go to the next slide, simply that we're living today. Okay, so this is a very simple way, but I think in a more fundamental way, this is the kind of thing that we're doing with the universe. We're trying to intercept the messages and then bring the laws of physics out of that. Next slide, please. So the Kapteyn-OmegaCEN group for data intensive astronomy and astronomical science data center for data science systems. I first want to introduce you. So Edwin already introduced in the beginning of this session the Astrowise system that we started out with. In the early 2000s, it saw its first light as a system and then started to do the data big data mission on the OmegaCEN wide field imager at the VLT survey telescope, in particular the degree survey in 2011. And we had spin-offs that we put this WISE kind of technology and paradigm of going back to the source, to the raw data, in a MUSE-WISE system. And MUSE is a spectral integral field unit on the very large telescope of ESO. And so that was then the MUSE project. It saw as a system first light in 2013, and then MUSE got commissioned and we started operating. And then now we're having the Euclid data processing system, which also contains this core of WISE technology that we're reusing. That saw us first light already a while ago, and now is going onwards to await the rocket, as Henk Hoekstra said, that we need to get Euclid into space. And then in looking towards the future, we're starting to build the first steps to a Mikado-WISE system. And Mikado is a near-infrared imager and spectrograph that will be positioned on the extremely large telescope of ESO, seeing its first operational light in 2027. And so these systems are distributed over Europe. This is a particular example of the AstroWISE system where the nodes are and is being coordinated here from Groningen. Here are some key numbers to give you a feel and a flavor for what they are. You can see that the AstroWISE and MUSE systems has a number of registered users, and we're in the petabyte regime with a lot of separate files, 200 million on that order. And the neural network or the brains of the systems is the database that describe all the data about the raw data and about the data, the bulk data, which is now getting into 12 terabytes and about 2 to the 10 records. And so we have locations of the hardware and the software and the people that are distributed over several locations. And then the big guy in which we are one part here in Groningen is the Euclid data processing system, for which we have a Euclid Science Data Center. And as Edwin said, there's 9 of these centers spread over Europe and actually also the US. And here you just see the slice of bulk data that we will take care of in Groningen, but we're also mirroring the full database, and that's why the 50 terabytes expected in the full database will be mirrored here in Groningen as well. So these are very impressive systems. Next slide, please. That we are using for big data astronomical science missions. As I said, the AstroWISE system is being used for studies of dark matter and dark energy with the kilodegree survey. Then the MUSE-WISE system is in general for extragalactic and galactic dynamics and stellar populations, because with integral field unit spectrographs, that is what you can go after by guaranteed time surveys with the instrument team. Then we have Euclid, which is after the understanding of the accelerated expansion of the universe and dark matter and dark energy. So well displayed in many of the talks yesterday by Henk and Leon, and now also shown visually by Reese today. And then Mikado, it's one of the projects that is under Reinhard Genzel originally. And so it has all to do with the Milky Way supermassive black hole as a driver of how Mikado is designed, but it can do actually, it's a workhorse. So it can do a lot about galaxy evolution and dark matter and exoplanets as well at the extremely large telescope. But the interesting thing is, and I won't have time to go into it, but these systems are data-centric systems, which mean they haven't been focused, to get out your weak lensing or to get out your globular clusters, but to describe the data that you're using to do this in the most data-centric and as close as possible to the data, the nature of the data itself. So in that sense, it's describing the data as accurately as possible and then building from that. In that sense, it has genericness. And so that's why we started also to think about, okay, could we use it for other purposes? And so one, close to home, of course, is something like the Cosmo weather that I discussed, these near-Earth objects and their impact hazards. But, and that's something I will not discuss today, and we're not going on that track yet in depth yet, but in principle, the way the data is modeled, it tells you an awful lot about the atmosphere. And so recently I got in contact with people that are interested in atmospheric studies using actually our astronomical telescopes. And that's the, all the things we as astronomers throw away, but these atmospheric people are very interested in it. And also fireballs that are in that atmosphere, they were interested to dig that out of our data. And so there's a couple of systems that are data sets plus systems that are in particular useful for near-Earth objects, and the other ones also for close stellar encounters that some of the people interested in long-term Cosmo weather are interested in. Next slide, please. Yes, so I will first bring you to the platform where the AstroWISE system gets its data from. as one of its primary surveys. So that's the kilodegree survey. Here you see the 4 nice sisters, large sisters, that are the very large telescopes. But the girl I'm really interested in is here on the side. And that's the VLT survey telescope. And actually all that data load is coming from that particular telescope. And so we can now go next. So this is on Paranal, for those that are not astronomer. It's a beautiful place. If you are in Chile, it's a couple of hours into the nowhere. And then all of a sudden you have in the middle of nowhere, you have this technology standing on the top of a mountain that's completely silent, have the Milky Way above you. And these domes that I call ballerinas actually start rotating in some kind of cosmic dance at night when you're out there. It's really beautiful. Now we go inside the VLT survey telescope. So you see the 2.5 meter telescope up here. It's in the weird projection, but it's a fisheye lens that we have. Here's the picture being taken. And here you see the system. And so at the bottom is actually the instrument, the camera, which we will now go into in the next slide. And here you see the OmegaCEN imager. So 32 CCD, science CCDs with auxiliary CCDs around it. And here you can see one example image. So it fits about 4 moons. And so that was early on in 2000s, and then 265 megapixels were quite a bit. Later on, more telescopes like this, because of this delay, got on. But the impressive thing that we're lucky about is that it really exploits the exquisite atmospheric conditions at Paranal. So it has really high image quality and a small point spread function that we're really exploiting, and that kept this machine in the competition for this weak lensing analysis. And now I think we will go over to my slides here, if I'm correct. Oh no, I wanted to show that now we have a little bit over a decade of observations coming in from OmegaCEN. And if you, can you drop the, yeah. Yes, still today, you can see all the pointings that the system did. So there's about 400,000 pointings since it started that you were just showing the southern hemisphere. So the pole that you're seeing is actually the southern equatorial pole. And here you can see all the pointings, the 400,000 pointings that OmegaCEN, or more than 400,000 OmegaCEN has taken until now. Okay, I think that is the last one, full dome, right? And now we go to my slides. So this is the data from which the kilodegree survey, it's among this. There's many other surveys going on, but the kilodegree survey was one of the largest in terms of time as well. And so many of these pointings are coming from there, and all the shape analysis using this exquisite full Earth half max of our point spread functions was done. Yes, so now I go over to this near Earth object business. And just to make you familiar a little bit in general, if you're not familiar, here you see 2 examples of these near Earth asteroids because they were visited by space missions. One is Itokawa. See, it's a typical size of 500 meters and can go up to the largest ones, which are 20 kilometers. And so this is the kind of Cosmo weather that's hanging above us as we cruise with our cruise ship through the Milky Way. But this is then nearby the Cosmo weather in our solar system. Of course, there are many pieces of rock that are much smaller than 500 meters and go down to meter size and so on. And then we lose sensitivity. Here's the sun. This is the picture of the solar system. Here's the orbit of Earth. And you can see different families of these near Earth objects that are either, they cross Earth's orbit, either going from outside to inside it, or almost exclusively inside it and then a little bit going to the outside, or more intermediate. So there's all these families. And this is what they look like in our images, if you know where they are. As you can, this is quite a difficult game to play to really read them out. So that's a project that we started to do together with ESA because they were interested to exploit our data, but then looking in particular at the near Earth objects that are in the risk list. The risk list is a list of about 1,300 objects that are considered that they have a non-negligible impact risk in the coming 100 years. And that's why they're of exquisite interest to ESA. Yes, now I can use my thing here. Yes, so here you see again the pointings that I was showing before. So that was our starting plate, these 400,000 observations that we can milk through. This is then the southern celestial hemisphere part to look for these near Earth objects on that risk list. So the prediction was Oh, I cannot do that here. Okay, I will tell you. So there's about 400,000 images in this, and 1 in 40, actually one of those risk list objects was passing. So 1 in 40, they are actually passing. So that's the good news, that there's potential, crossings of these in quite a number of our observations. But the bad news is that many of these are very small or very faint, because they're in a distant location. And so only in 68 we predicted, after going through all the analysis, that we would be able to detect them of all these pointings. So these are the predicted crossings that happen. Really, they are there, but you just don't have the sensitivity with our single exposures. But these 68 we do have. And so out of these 68, we managed to refine 47. And I will not go into the details. It has to do with the accuracy of these predictions, but also the signal to noise estimates that you predict for different families of these near Earth objects. But these 47 actually we did detect. And here you see the results of this harvest for these only these few objects of these near Earth objects that are on the risk list. In total, there are about 20,000 NEOs, but there are 1,000 plus on this risk list. And so 47 we detected, 27 were by an automated pipeline, and 20 more we gathered actually by visual inspection. And they included the precoveries for 3 NEOs, near Earth objects. Precovery meaning that you actually find out that in your archives there is an observation of this object before it actually was properly detected to be such an object, and significantly away in time, so that you observe it at a different set in its orbit and therefore get a much improvement in the orbit determination. And so for a couple, we got these orbit improvements. And if we go to the next slide, you see that actually for these 3 that were precoveries, all of them proved to be an improvement in the astrometry and therefore the orbit that we immediately could rule out. They were kicked out of this risk list. So for the 3 that were precoveries, they all managed to kick them off of this risk list. So that gives us hope from this pilot project that we should continue doing this on different data sets, combining different data sets to increase the signal to noise in case you have more data on at the same location. For instance, in the near infrared with all the short exposures, you won't see them. But if you start to stack them correctly, you will see them. I pointed in red that these are small objects. One is 80 meters, the larger one. And then if you compute the impact kinetic energy, it's on equal par with the Tsar Bomba, one of the largest nuclear explosions that Russia ever tested. And you can see that, for instance, there was one very small object for which we had an increased risk. So it's not in the risk list, but it increases risk, but it's only 3 meters. And that proves, we have sensitivity if you're in the right spot at the right time to really detect these small objects. Okay, now I step out from this astronomical perspective and human-centered perspective, and I started to think because we're at this conference, if I were information, somebody that I have nothing to do with humans, but I look at what these humans and their information systems are doing together. And then this is the following that I saw. You have a photon ocean out there, and then these humans combine with systems together to make an optical to digital compression system, right? That photon ocean, and we compress it because we distill the photons out of it that we're in particular interested in, and we don't pay attention to the photons we're not particularly interested in. And in this case, we ended up with about 40 terabytes of raw digital data. In our case, we put this as humans into an asteroids system, so an information system, and then we started to combine that system with another existing system, namely the Gaia system, which has this exquisite astrometry on a lot of objects that were observed in this photon ocean. And that's a Gaia data release 3 data, which is about 1 gigabyte. And by that combination, by in some sense combining or entangling, perhaps I even dare to say, we got out this combination that we could improve our understanding about these bits that we were interested in, namely these astrometric positions. So we ended up with 47 times 6 bytes out of 50 terabytes that helped us to put it into yet another system, an impact probability calculator, where also goes in a lot of knowledge about Newtonian gravity and non-gravitational physics, because there are effects well, I'll discuss that a little bit later, on these asteroids that perturb their orbits. But that's then, and I could continue, but I don't, in the sense of time, you can continue that we see that if you're looking for information from an information perspective, you see these humans that are helping machines, if you portray it provocatively, that are actually helping these machines to do all of this analysis. And I could foresee that if you're interested in futurism, that at some point these machines and these information systems don't need these humans anymore to connect them together, but they will connect, they can start being connected as some kind of internet and do all kinds of things without our direct orchestration of that. Anyway, that was the loose thoughts that I had. So now in the last 2 minutes about my idea of information decay and expiration is just food for thought in the break afterwards. In general, I started to think the information that I'm gathering in this near-Earth object hunt for this impact risk analysis has to do with a little bit how relevant it is. And by general, I mean, I was thinking in very general sense of the relevance of information going from astrophysical laws or laws of physics to even the info that you get in the New York Times. They all have a temporal dimension along which they either expire or decay, right? Some news is only news for a couple of hours and then it's already expired. There's a spatial dimension. It only matters to certain people. And also, if you think about life and intelligence, it's certain life forms that are interested in particular information. And physics and laws, of course, they spread a lot of temporal dimension. They're valid almost some of our laws, we think, throughout time and throughout the universe. So high temporal and spatial persistence instead of decay. And they're relevant for everything that lives. So they're very high on the standard. Whereas news about Trump, for instance, not that many people find it very interesting for a very long time and not in a very large region. They just get annoyed by it. Back to the new precoveries. So when I started to think about my temporal decay is that I have this orbit accuracy decay. I now know the orbit's quite accurate, but it's with a limited knowledge on all the astrometry. So over time, my prediction of this impact analysis will decay. And so in addition to that, we have these non-gravitational forces like the Yarkovsky effect and the Yorp effect and chaoticism in the system gravitationally as well, that will make them deteriorate. So we have to continue to update our information if we want to stay on top of this impact hazard analysis. Spatially, it's only relevant for us here inside, the asteroid belt, because that's where they are, and outside it is already pretty irrelevant. In terms of life forms, we're doing it because we are interested to survive as a species, but in some sense, we're doing this, for all of life, I think, that we say we want to have the impact hazard analysis for life on Earth. So we're just foods for thought for the break. And I will leave that with this summary that I think that the NEO risk monitoring in some sense has parallels with distilling and lossy compression of information. And I want to come back to Edwin's book, Powers of Two, where also in Joyriding the Universe section and the entanglement section, you see much deeper thoughts about this. And then let me end to say that for me, it's a pleasure to make this hat trick today. That is the fact that I'm working now with these asteroid systems, these WISE systems, for which the originator is Edwin, and staying in a dome to talk about them, for which Edwin is the originator, and then doing that in a conference that is a Target Field Lab organized conference, of which Edwin is the originator. So I'm happy to make this hat trick together with you, Edwin. Thanks.
Okay, well, thanks a lot, Gijs. And to both Gijs and Luis, my enormous appreciation for, at the same time, running this conference and also giving a talk, so that I know how difficult that is. So thank you very much for doing that. So there's time for one question. And if you are raising your hand and I don't see it, then yell. Please.
I see Charlie.
Ah, there's Charlie. Yes, please.
I was wondering whether you're making any progress on, you mentioned the orbital decay, and you mentioned the Yorp and Yarkovsky, and then chaoticism. I don't know what that is, but are you making any progress in predicting or correcting for those systematic errors by knowing something about the spin or the albedo or outgassing of these objects so that you can, in the future, know how to get a better orbit for new ones that might be more urgent?
Yeah. So first, to your first remark about chaoticism, that is about the much longer term effect, right? That if we now know the orbit of Mercury, or its position and its velocity to exquisite precision, even then it will decay into an unknown after about 100 million years, I think, in a chaotic bandwidth that we don't know, cannot predict its ellipticity anymore.
Right. You're citing Jacques Lescar's work on this?
For instance, yes, that kind of work.
Mhm.
To come back to the other question is, yes, we're making progress. So one of the next steps will be to combine infrared and thermal infrared data with the data that we have, so that you can get a hold on the Europe and Yarkovsky effect, and then make actually predictions on the orbits, including Europe and Yarkovsky. But it's early days for that.
All right, given the time, we're already running out of time for this session, which is of course my fault. We can go now for coffee and tea, but first thank Gijs again. And I propose we reconvene at 4, which is a little bit later than originally scheduled. At 4, we come back, and then we will have a talk by Larry Wasserman, which is really one of the high points of this conference. So see you in a minute.